Okay, so the second thing we want to talk about are critical points and increasing, decreasing intervals. And this is where I really think calculus gets fun and exciting and really shows its power, is in the ability to determine when is a function increasing or decreasing and where does a function have maximums and minimums. Okay, so very important definition here, so I'm going to highlight it. Definition: let f be defined at c if f prime of c is equal to 0, or if f prime of c is undefined, then c is called a critical point of f. And sometimes we call these also critical numbers. Okay, so critical numbers, some textbooks will use that terminology as well. Okay, so example 2, we want to find the critical points of the function. So f of x is equal to 1/3 x cubed minus 2 natural log of x. Well, in order to find critical points, I have to take the first derivative. So f prime of x is going to equal to x squared minus 2 times the derivative of natural log of x. I remember that the rule is u prime over u. In this case, u is just x, and so the derivative is 1 over x. Okay, well that will clean up to x squared minus 2 over x. Now remember, critical points come whenever the derivative is equal to 0, so in a minute I'm going to set it equal to 0, or when the derivative is undefined. And what you should notice here is that there is a denominator for this derivative right there. So basically, in order to determine where f prime is undefined, we need to figure out where is that denominator equal to 0. Well, if I set that denominator x equal to 0, I get my first critical point, which is just x equals to 0. Okay, so that's my first critical point. I'm going to highlight it in yellow so that you know it came from the fact that the derivative was undefined at that point. Okay, the next thing we want to do is set this equal to 0 and go ahead and solve for x. So if I move over the 2 over x term and then multiply both sides by x, what I'm going to be getting is x cubed is equal to 2. And to get x by itself, I'm just going to take the cube root of both sides. So x is going to equal to the cube root of 2, and that's going to be my other critical point. And that critical point came from the fact that the derivative was equal to 0. Okay, so make sure that you are checking both. You need to make sure that your derivative is defined, and if it's not defined, then that particular value is called a critical point. Okay, example B, we have x squared plus 1 times e to the x, so this is going to be a product rule in order to find its derivative. So f prime of x is going to equal to the first, multiplied by the derivative of the second. The derivative of e to the x is just e to the x, plus the second, e to the x, multiplied by the derivative of the first, which is 2x. So, sorry about that, let me erase that and put here 2x. Okay, if I factor out an e to the x, then this is going to say x squared plus 2x plus 1, and I'm going to set that equal to 0. Notice there aren't any denominators going on in this derivative, and so we're not going to have any critical points for which the derivative is undefined. Okay, if I go ahead and factor the parentheses, then that's going to say x plus 1 squared, and I'll let you verify that on your own. And we still want that to be equal to 0. So what we do is we take e to the x and set it equal to 0, and also x plus 1 squared and set it equal to 0. Well, that's going to give me x is equal to -1 right there. And e to the x equals to 0 doesn't give me anything, because if I were to take the natural log of both sides, I'm going to get x is equal to the natural log of 0, and the natural log of 0 does not exist. And so because of that, we don't get any critical points from this part. We only get our critical points from x equals to -1, which was this part right here. Okay, so because the first derivative represents the slope of a function, it is able to tell us whether a function is increasing or decreasing on a particular interval. So that's what this theorem 3.5 says, is that if f prime is greater than 0, another way to say that is if f prime is positive, then f is increasing. And that should make sense to you, because if f prime is positive, that means the slope of the tangent line is positive, and so that means that the function should be increasing. Secondly, if f prime is less than 0, or we could also say negative in that case, for all x in AB, then f is decreasing. on AB, and that should also hopefully make some sense to you, since a negative tangent line would look something like that, and that would mean that the function is decreasing. Okay, so this picture kind of represents what's going on here and kind of shows you how the derivative is related to the slope of a function. Okay, so this leads to another just incredible idea that we get from calculus, and it's called the first derivative test. So let C be a critical point of a function f that is continuous on an open interval that contains that critical point. If f prime of x changes from negative to positive, and another way to say that is if f prime changes from negative to positive, that means that f changes from decreasing to increasing. And I know that if a function changes from decreasing to increasing, then I'm going to get a relative minimum. Obviously, I drew the wrong thing there, so I'm going to erase that and draw what I meant to draw, which is go from decreasing to increasing, which creates my minimum. Okay, similarly in number 2, if f prime changes from positive to negative, what that means is that f changes from increasing to decreasing, and what that does is it creates a maximum point. Okay, so hopefully that makes some sense to you. It's a really intuitive thing that I think makes a lot of sense once you kind of understand what exactly this is saying. Okay, and then thirdly, it says if f prime is positive on both sides of C or negative on both sides of C, then f of C is neither a relative max or a min. And so really what that's saying is that if f prime does not change signs, then we do not have a max or a min. So f prime doesn't change signs, then what that means is that we have neither a max nor a min. Okay, so example 3, we want to find the intervals where f is increasing and decreasing, and then also find the local maximums and minimums. So letter A here, we have f of x is equal to 300x minus x cubed. So the first thing we need to do is find our critical points. That will come from taking the derivative and looking to see where is it undefined or where is it equal to 0. So the derivative of this function is going to be 300 minus 3x squared. Well, that's just a polynomial with no denominators going on, and so because of that, this derivative is going to be defined for all real numbers, and so I don't have any critical points where the derivative is undefined. But if I set it equal to 0, I am going to get a couple of critical points. Okay, so what I'm going to do is I'm going to factor out a 3 from both of the terms here, so that's going to leave me with 100 minus x squared equals to 0. And then what I notice in the parentheses is that that's a difference of squares. So this is going to be 3 multiplied by 10 minus x times 10 plus x. Okay, and what that does is it really helps me to see what exactly the critical points are. I can now see that the critical points are 10 and negative 10. Okay, so what I'm going to do with those points, because I'm not sure if they're maxes or mins yet, I'm going to put them on a number line and then test intervals to see if the derivative is positive and negative in those sections. Okay, so here's negative 10 and positive 10, and what I'm going to do is I'm going to check numbers from each interval here to determine if the derivative is positive or negative. Okay, so in this first section, I could try negative 11, or really anything that's less than negative 10. And if I plug negative 11 in for x, I'm going to do it in the factored form, this factored form right here of the derivative. That's going to make it easier for me to determine what the sign is. Because remember, I don't really care what the value is. I really just care, is it positive or negative? Okay, so if I plug in negative 11, 10 minus negative 11 is a positive, 10 plus negative 11 is a negative, and a positive times a negative is a negative. And so in this section, the function is going to be decreasing because f prime was less than 0 or negative. Okay, in the second section, we could choose 0. That's typically the value that I'm going to choose just to make things easy on myself. So if I plug in 0 for x, 10 minus 0 is positive, and 10 plus 0 is also positive, and two positives are going to make a positive. Okay, and then for anything greater than 10, we could certainly plug in 11, And if we plug in 11, then 10 minus 11 is negative, 10 plus 11 is positive, and a negative times a positive is negative. Okay, so this is now going to allow me to write my answer. So I'm going to write down that this function was increasing on the interval from negative 10 to 10. It was decreasing from negative infinity to negative 10, and also from 10 to infinity. And then I also have one max and one min. So I have a max wherever the derivative went from positive to negative, and that would be at x equals to 10. Okay, and if you notice the chart, it really kind of helps you determine where the maximums are, because you can see here the derivative went from the function went from increasing to decreasing, and so that's how we had a maximum created right here at this point. So this was a max. Okay, and then similarly, we're going to have a min at x equals to negative 10. For the opposite reason, the function went from decreasing to increasing here, which created a minimum at x equals to 10. Okay, example B, g of x is equal to 1/3 x cubed plus 3/2 x squared minus 70x plus 5. I'm going to work through this one a little more quickly, only because it's very similar to example A. So the derivative is going to be x squared plus 3x minus 70. Again, there's no denominator here, so I just need to set it equal to 0 to find my critical points. And if I factor this, I need factors of negative 70 that add to 3, and that would be x plus 10 and x minus 7. Okay, so that's going to give me the critical points, x equals to positive 7 and negative 10. I'm going to put those on a number line, so negative 10 is going to go here, positive 7 will go here. Okay, in the first section, if I want to plug in negative 11, the first factor of the derivative is going to be negative, the second factor is also going to be negative, and so a negative times a negative will give me a positive. In between negative 10 and 7, I could choose 0. If I plug in 0 to both of those, I'm going to get a positive times a negative, which of course is a negative. And then after 7, I could plug in 8, and if I plug in 8 to both of those, they're both going to be positive. Okay, so this function is increasing on the intervals from negative infinity to negative 10, and also from 7 to infinity. It is decreasing in the middle there from negative 10 to positive 7. We have a maximum point wherever the derivative went from positive to negative, and that would be at x equals to negative 10, and a minimum, in this case, at x equals to 7.